this video, we're going to go over first order linear differential equations. But I'm going to start off with the simple part, which is let's look at something that we are familiar with. With separable equations, we have the following. dy dx equals f of x times g of y. And what made this so easy for us is we could easily separate these variables because on the right-hand side, we have a product of the two different functions. So we could just group the y's together and group the x's together and call it a day. But the question becomes, what if it's not separable? Are there other types of diff EQs? And the answer is absolutely. All right. In fact, one of them, quite frankly, one of the most famous is one that we're all familiar with, which is Newton's second law. Okay, we are all familiar with this. A lot of people, though, look at it as F equals ma, or F equals mass times the second derivative of displacement with respect to time. All right. But we're gonna actually look at it the way that it's meant to be written, okay? So first things first, we're still gonna have F equals ma. It's just I'm gonna write ma as mass times the derivative of velocity with respect to time. So this right here is our ma equals. Now, when we write F, what we really mean is the sum of the forces, or all the forces involved. Okay, it's just we just write F, but you got to think about what's really happening. So a really good example is just to have like a tennis ball. All right, when a tennis ball falls back down to the earth due to gravity, there are actually two forces, and I'm not telling you anything you probably already don't know. The first force is gravity, and we know that. Now, gravity we can define as negative m times g. All right, and it's negative because it's moving downward. We are establishing positive y direction. But the other force, and this is the one in a traditional physics 1 course, this is the force that you normally ignore. And that is going to be air resistance. We are no longer going to ignore air resistance. So, on the right-hand side, instead of writing F, I'm going to write the sum of the forces. So, we get negative kV minus mg, where kV is the force of air resistance, and it's operating opposite of the force of gravity. All right, so this is basically what we have here. And if we assign some arbitrary initial values, in other words, if we know the velocity at time 0 equals the initial velocity, we have our very first linear differential equation. So let me go ahead and actually define what a linear differential equation is. So a first order, and I'll explain what that is in a second. So your first order differential equation is linear if it can be written in the form a of x times y prime plus b of x times y equals c of x where a of x, b of x, and c of x are all arbitrary functions of x. So this is a first order linear differential equation. But now we got to understand, okay, we could see it. You could probably put this down on a flashcard, but if somebody came up to you and said, "Why is it linear?" Here's why it's linear. First, well, yeah, let's start with this. Why is it first order? Because you have a first differential or first derivative. That's why it's first order. But what makes this linear? All right, and this is going to look weird initially, but I'm going to show you. What makes this linear is the fact that this differential, y prime, is raised to the first power. So that is what makes this linear. All right? Now, there are all different types of examples, all right, of linear first order differential equations. So here are some examples. So examples of linear first order diffs. And you're going to notice a common theme with all of them. Here's the first one. The quantity 3x to the second minus 4 times y prime plus the quantity x minus 3 times y equals sine of x. So this is a linear first order. Here's another example. Sine x times y prime minus cosine x times y equals cotangent x. This is linear, all right? Now, I'm going to show you two examples of nonlinear. Let's see if you could spot it. So here's the first one. Y prime raised to the fourth plus y equals the quantity 3x minus 2 times the quantity y plus 4. And then the second nonlinear would be y prime to the second equals sine of y plus cosine of x. Now, hopefully you could see why these are nonlinear. The big reason in the first one is right here. You have a first order differential, y prime, but it's raised to the fourth power. So that's no longer linear. Think about what a linear equation is in algebra. A linear equation is when the exponent is raised to the first power. All right, same thing here. Our differential is raised to the fourth, therefore it's nonlinear. Down below in the second example, we have the differential raised to the second, but also this term right here, because the y is included within the transcendental function of sine, that makes it nonlinear as well. Now, you'll study a lot more of these when you get into differential equations, which will be like in a semester and a half or two. All right, so just kind of be able to recognize them. Right now, the big thing is going to be how do we actually solve our differential, our first order linear differential equations. Okay, so in general, a first order linear diff EQ has the form, and I'm just rewriting the definition here. All right. A of x times y prime plus b of x times y equals c of x, where a of x, b of x, and c of x are all functions of x. They can even be constants, okay? But the big question now becomes, how do we solve this? All right. And the first thing that we want to do, and I have some steps here for us, but first thing we want to do is we want to get this into what we call standard form. All right, so here's how we do this. It's very simple. All you have to do is divide every single term by the arbitrary function in front of the y prime. By doing that, it gives us y prime plus b of x over a of x, y, equals c of x over a of x. Now, I'm just going to go ahead and make like a little substitution, and I'm going to say p of x equals b of x over a of x, q of x equals c of x over a of x. And the only reason why I'm doing this is so it just looks cleaner. And here is our standard form of a first order linear diff EQ. Now, this may look very simple, and I agree with you, it is. All right, all you gotta do is just divide by a of x. But there's actually something happening here. And I don't know if you can see it, but on the left-hand side of this equation, we kind of have a little something something here. And what I mean by that is this looks like something that you and I are both familiar with. And that is the product rule. It's not exactly the product rule yet, okay? But it's actually pretty darn close. I mean, if you think about what the product rule is, when you have two functions and you want to take their derivative and they're being multiplied, all you do is just apply the product rule, f prime g plus g prime f. And if you could see here, we kind of have that, all right? So the big question is, well, how do you get this? So I guess really what we're asking here is there a function such that its derivative is the same, and I'm going to put this in quotation marks, it's the same thing. In other words, the derivative is basically going to be the same exact thing as what you start with, but only differs by a constant. All right? So if you think about all your derivatives, like the derivative of x to the third power, well, that's 3x to the second. All right? Notice you're not starting and ending with the same thing. You start with x to the third, you end up with x to the second times 3. They're not the same. All right? But there is one function that we have studied that when you take its derivative, it's the same exact thing. And that function is e to the x. Because the derivative of e to the x is e to the x. So now the big question becomes, can we use this to our advantage? In other words, is there some way that I can incorporate that up into here? Because like I said, you got almost a product, or what you're missing is this function. You're missing some unknown function here that will fill in your product rule for you here. All right. And the answer to my question is yes, there is something that we can do. All right. So I'm going to go ahead and I'm going to show you how this works. All right. It's not difficult. It's just a matter of following steps. Okay. So the first thing we're going to do is we're going to start with y prime plus p of x times y equals q of x. Now, like I said, we know on the left-hand side here, we kind of got that product rule, but we're missing that function. So let's call the unknown function We'll just call it u of x. So what I'm going to do is I'm going to multiply the entire equation by u of x, because I'm totally allowed to do that. I mean, that is just the multiplication property of equality. So multiply the left by u of x, and multiply the right by u of x. Okay? So, excuse me. So now what we're going to do is we're going to go ahead and start labeling things. All right? So, if we think about our product rule. Okay, if we think about the product rule, we know the derivative of f of x times g of x is going to equal f prime of x times g of x plus f of x times g prime of x. So we're going to let y equal f of x, g of x equals u of x. Okay? So what I'm doing here is I'm already starting to make some of these substitutions here. All right? But the big question here is, what do I do with this g of x equals u of x thing? All right, that's the big question here. So give me 1 second here. Let me, get back here. All right. So when we go ahead and we start matching these terms, okay? If we take the derivative of g of x here, all right? So the derivative of g of x is going to be u of x times p of x, because you got to remember, we kind of have this product rule going on up here. So this right here is this whole thing right here. So the derivative of this, all right, is going to be g prime of x equals u of x p of x. And this leads to u prime of x equals u of x p of x, because we are saying u of x is g of x. Therefore, the derivative of u of x is going to be the derivative of g of x, which is u of x p of x. Now, what we can do here is say we're going to divide both sides by u of x to give us u prime of x over u of x equals p of x. Now, I know this looks a little crazy initially, but just watch what happens. We are trying to find this unknown function that is going to allow us to fill in the blanks for the product rule. The unknown function is u. But what I can do here, with what we have here, notice this is separable, and it's already separated for us. So what I'm going to do is I'm going to take the integral of both sides. I get the natural log of u of x on the left. On the right-hand side, I get the integral of p of x dx, because I don't know what p of x is. To solve for u of x, we're going to exponentiate both sides. All right. On the left-hand side, I'm basically left with u of x. On the right-hand side, I'm left with e to the integral of p of x dx. Now, there is a plus c in there, but I'm omitting that only because we really don't need it here. What we're really looking for is this thing right here. And this is called our integrating factor. All right? And what this does is this tells me what the unknown function to complete the product rule is going to be. And I just did this by recognizing that when I took the derivative of u of x, that is the derivative of g of x, and g prime of x in this case is going to be u of x p of x due to the product rule. All right, remember the product rule. That's what this is all about. So this is like f prime g, g prime f. Like I said, it looks a little crazy at first, but you gotta work with this a little bit. Okay. Now, getting back down to here, what can we do with this? Well, what we can do with this, all right, excuse me, is we can go ahead and start solving all of our linear first order differential equations by using this. And here are the steps right here. I already have them written out for us. Oh, what is that? That is it. It's just enormous. There we go. So here are our steps. Step 1, when you have a first order linear diff EQ, you're going to put it in the standard form. Step 2, you're going to find your integrating factor. All right, this is that unknown function that you're looking for. So you want to identify what p of x is, take the integral of that, and make sure it's raised to make sure you exponentiate it. All right. Step 3, you're going to multiply both sides of the differential equation by u of x. All right. Step 4, you're going to integrate both sides and then divide by u of x. All right. Now this step probably here, step 4, probably makes no sense right now, and that's okay. I'm going to show you. And then in step 5, you're going to determine C if you have initial conditions. So at the end of the day, here's what we have. In this first step here, notice I multiplied everything by u of x. That's right here. Highlighted in this nice purple color is my standard form of my first order differential equation. Okay? Now, on the left-hand side, if I knew what u of x was, and I simplified this, you would end up getting the product rule. And the product rule of what, you may ask? Well, that's going to be the product rule between, or it's going to be the derivative of u of x and y. I mean, if you look up above here, all right, you have u times y prime, in this case is going to be g prime. This entire thing is g prime. Oops, sorry. Got these backwards. Sorry, my bad. I got these backwards. That's g f prime g prime f. All right. So that's what I was demonstrating up above. All I did here, what I mean by here is, here in this nice purple color that I'm highlighting, all this is saying, this is just shorthand for take the derivative of two different functions. When you do that, you apply the product rule. Now, we integrate both sides. Okay, so we integrate both sides. That is going to be step 4. And when you integrate both sides, you get u of x times y on the left-hand side equals the integral of u of x, q of x, d of x. Just two functions. You don't know what they are, but we're going to leave it like that on the right-hand side. And then when I said you divide by u of x, you divide by u of x. We'll write it out front here. You divide by u of x to solve for y. And that's exactly what we get here. So if you think about what I have on the board here, once you recognize you have a first order linear differential equation, right here's the formula. Y equals 1 over u of x times the integral of u of x, q of x times d of x. Like, that's the formula. So it's best now to show you an example, to show you how this actually works. Because when I was a student, a bunch of u of x and p of x and q of x's all over the board was a little confusing at first. So what I want to do here is I want to do this example. So we're going to solve xy prime plus 3y equals 4x squared minus 3x. And we'll assume x is greater than 0. All right. Step 1. Standard form. So let me just rewrite this. And then we're going to divide everything by x. That's going to give me y prime plus 3 over xy equals 4x minus 3. Now just to label things so we can see everything. 3 over x is going to be p of x. The quantity, 4x minus 3, is q of x. So we're in standard form. Step 2. We want to find our integrating factor. Now remember, that's that unknown function that once we find it, we're going to multiply the entire differential equation by that. So for us, it's going to be e to the integral of 3 over x dx, which I'll write as the integral of, I'm going to rewrite it as e to the 3 times the integral of 1 over x dx, pull the constant out front. The integral of 1 over x is the natural log of x. Apply my properties. I'm going to get e to the ln of x to the third. And that reduces all the way down into just x to the third. Now, remember, that's our integrating factor. That's what the IF stands for, okay? At the start of this, I said we need to find that function that when we multiply the entire equation by it, we end up getting the product rule. Watch what happens here. Step 3. We're going to multiply both sides of our equation by the integrating factor. All right. So I'm going to keep this nice and simple first. So we're going to multiply everything by x to the third. X to the third times y prime plus x to the third times 3 over x times y equals x to the third times the quantity, 4x minus 3. Now the right-hand side of the equation is very simple. You get 4x to the fourth minus 3x to the third. That's real simple. But it's the left-hand side that creates all the beauty within this method. Because when you simplify, we get x to the third times y prime plus x to the third times 3 over x is 3x squared times y. And if you look at the left-hand side, this is nothing more than the product rule between the derivative of your integrating factor and y. Because think about it. If x to the third is f and y is g, and we know, and I'll write it like this to keep it nice and simple, f g prime plus f prime g, notice that's exactly what you have up above. F g prime plus f prime g. That is what the integrating factor does. It takes something that kind of resembled the product rule and actually makes it the product rule. Now from here, we're going to go ahead and we're going to do step 4, which is integrate. So integrate d dx of x to the third y equals the integral. Oh, forgot my dx. the integral of 4x to the fourth minus 3x to the third dx. On the left-hand side, the differential and the integral, they like cancel each other out. So you're just left over with x to the third y equals. On the right-hand side, you're going to get 4 over 5 x to the fifth minus 3 over 4 x to the fourth plus c. And then we divide everything by that unknown function and solve for y, which gives me y equals 4 over 5 x to the second minus 3 over 4x plus c times x to the negative 3. If we had initial conditions, we would go ahead and do step 5, but in this case we didn't. So this is where we stop. So I hope this helped, and I hope it made a lot more sense than a traditional proof, what I did earlier. So let's go ahead. I'm going to do another one here. All right, in this one here, I'm going to do an initial value problem. So we're going to solve y prime plus 3y equals 2x minus 1, where the initial conditions are y of 0 equals 3. And with this, I'm going to kind of speed up a little bit. So we got step 1. All right, standard form, already done. We love that. Step 2, find our integrating factor. Well, in this case, it's just going to be e to the integral of 3 dx, which turns out to be e to the 3x. And that's as far as you can simplify it. So what we're going to do here, step 3, is we're just going to multiply everything by e to the 3x. So we get e to the 3x times y prime plus 3e to the 3x times y equals 2e to the 3x. Actually, let me write it as 2x e to the 3x minus e to the 3x. Okay? Once again, notice you got the product rule. It's right there. So let's go ahead. Let's simplify this a little bit further. We know the product rule is going to be between our integrating factor and the variable y. And on this right-hand side here, there's really nothing I can do in terms of, I guess, in terms of simplifying. So I'm just going to leave it like this. All right. Now step 4. This is where we got to integrate everything. So integrate the left side. Integrate this right side. All right, here we go. Now this is going to be really interesting, because on the left-hand side, that's very easy. You get the integrating factor, e to the 3x and y. But on the right-hand side, you get a little bit more work ahead of you. And the reason, hopefully you're looking at this going, uh-oh. You're going to have to do integration by parts there. So because I don't want this video being too long, I'm going to just go ahead and tell you what the integral is. So you end up getting 2x e to the 3x minus e to the 3x all over 3 minus 2e to the 3x over 9 plus c. All right, so you can go ahead and you can do that. It's not that bad. It just takes a little bit of time. Now, we're going to divide everything by e to the 3x. Oops, there we go. And let's go ahead and, you know what? I'm going to write y equals. Now, be careful with this, because technically, and I'm going to just write it like this. That's e to the 3x, 2x minus 1, all over 3, divided by e to the 3x, minus 2e to the 3x over 9, divided by e to the 3x, plus, and I'm just going to write c e to the negative 3x. And the reason why I told you, I wanted you to be careful is these will end up reducing. They just end up reducing. So you're going to be left over with y equals 2x minus 1 over 3 minus 2 over 9 plus c e to the negative 3x. And you can go ahead, separate and group like terms to give you y equals 2 over x, or I'm sorry, 2x over 3 minus 5 over 9 plus c e to the negative 3x. And the last thing we need to do, which is step 5, in this case is find c given what was it, y of 0 equal 3. Is that was that the initial conditions? Yeah, y of 0 equals 3. All right. So that is just substituting it in. 3 equals 2 over 3 times 0 minus 5 over 9 plus c e to the 0. And when you go ahead and you solve, you get c equals 32 over 9 for a solution of y equals 2/3 x minus 5 over 9 plus 32 over 9 e to the negative 3x. And that is how we solve, like I said, first order linear differential equations. I hope this helped, and I will see you in the next video.